screen so that we can move on. Okay, hello once again. My name is Mugabe Samuel, and I'll be taking you through this first assignment for computer vision. Question one was about edge detection, and just before we dive into edge detection, we have to define what an edge is. And as you can see that it is an abrupt change in intensity of the pixel. As you can see the image on the left, what you call an edge, for example, at the edge of the coat of this gentleman here, there is a change in intensity, in the pixel intensity. That's why the computer program defines that as an edge. It sees that as an edge and it detects it as an edge. Now, of course, edge detection is very important. It is from edge detection that we are able to identify objects and images, detects all other images and objects in an image. Now, methods for edge detection, there is Sobel operator, there's Prewitt, there is Canny edge detector, which is the most commonly used, and then Laplacian and Gaussian. But we're going to discuss all this in the below next slides. So the Sobel operator, the way it works, it has a filter, what we call a filter, and it applies this filter and gets a value that is not so big. If the intensity is very big, then that edge is detected. If the intensity is small, then there's no edge. It has two filters, that is the horizontal and also the vertical, just as you can see. So you multiply this and then you add those values. You multiply this matrix, multiply it with the image, and then you add. Once you get a very big value, and it shows a change in intensity. Once the value is small, it shows a small change in intensity. That is the Sobel operator. Now, in the Prewitt operator, it also uses a mask, a 3x3 mask. It's a bit similar to the Sobel filter, though it's a bit less expensive computationally as compared to the Sobel operator. Now, the Canning edge detector, just like I told you earlier, that it is the most commonly used as compared to all the others. And the steps of using the Canning edge detector, you first smooth the image to reduce the noise. You can use Gaussian smoothing, whichever of your choice. Then you calculate the image gradient. Then it is from this image gradient that you apply the non-maxima. You apply non-maxima suppressing, which is sort of reducing the number of detected edges in an image so as to remain with the more accurate one. Then you use hysteresis thresholding, which is just a threshold. Below this value, it's not an edge. Above this value, it's an edge. Yeah, mainly that. Then we move on to corner detection. Of course, what is a corner? It is changing the intensity gradient abruptly in multiple directions. An edge, it's usually in one direction, but a corner, it is in multiple directions. So corner detection is identifying those corners in an image. Now, it is out of corner detection that we can use to detect object boundaries, tracking features in videos, for example, CCTV footage, and also identifying distinctive points in image registration and matching images, face detection, and also fingerprint detection. So corner detection, once you're working with corner detection, you have to work with what we call points of interest. these points of interest are distinctive parts in an image, points, distinctive points in an image, and these have these following features. They have to be distinctive, they have to be repeated. You can identify these points in repeatedly in either an image or in many consequent images. Localization, you can point this interest point onto a specific point. It's localized. You can get its address. It is localized somewhere. And then also invariance. Then application of these interest points, there is image matching, you've seen Google Photos, whereby you just click on someone's face and then they bring for you all your images of them. That is image matching. Object recognition, recognizing that this is a cat, this is a panda, this is a dog. All these, they use interest points. Image stitching, you've seen panoramas, those long photos of long landscapes. They stitch these images with help of interest points. Structure, motion, tracking, tracking motion. Let me say a car is moving in a video, tracking that motion, and also augmented reality. Now, there are many types of, many methods used for corner detection. The first one is the Moravec corner detector. Now, in this one, there's a window, you have a window, and it is to this window that you calculate the squared intensity difference between the central pixels and its neighboring in all directions, vertical, horizontal, and diagonal. Then from there you get the minimum sum of squared differences. Now it is from this minimum sum that you calculate the cornerness measure. Is it a cornerness measure? It's what we call the cornerness measure, as to which it is computed. Now, once you get that cornerness measure, you apply a threshold. By applying a threshold, it's simply saying that above this, you declare that a corner, a strong corner, then below this, don't declare that a corner. Next, we have the Harris corner detection. This one is relatively more common than the others. And as you can see, the image below, the image above, the one on the right, I think is the one which was detected using the Harris corner detection, because in there is non-maximum separation. That's why the one on the right has very many dots. But once you apply non-maximum separation in the Harris corner detection, of course, the corners detected are fewer. Yeah, so first you calculate there's a gradient calculation to find out the intensity, both horizontally and vertical direction. Then also there's what we call structure tensor, in which the gradients they create a tensor, structure tensor pixel. It's like a small matrix that summarizes how the intensity changes around that pixel. Then from there is the Harris corner response. Now this Harris corner response, it's a number that tells you how a pixel is likely to be part of a corner. It sort of tells you that maybe this pixel might be next to or part of that corner. And then, of course, thresholding. This is not a new term we've been talking about earlier, where you apply a threshold. Above this, it is a strong corner. Then below this, you don't consider that a corner, and it is ignored. And then from the corners you detected, you apply non-maximum separation, from which you drop the least expected corners. Instead of having very many detections of the same corner, you identify only the strong ones, and then you drop the others. Okay, so from this we had the practical. The next part was the practical part of the assignment. They're telling us to write, a function that convolves with that filter. I used here, I used Spider and Python. Was importing CV, that's a must. Import CV, and then from that you get that. So let's apply this and see. Where's the image? Okay, I've used image 4. Uh, I think let's first apply it, the function on this array here, numpy array, so that you can easily see what it's doing. Okay, there you go. So when you apply it on that, you get 90, 200, 210, as you can see there. But then I think let's apply it on, okay, let's apply it on a real image. Let's try and apply it on a real image. Okay, yeah, this image here. Yep, works well. It's convolution for you. I try to represent it here, though I needed to show it in practical terms. Okay, then we have edge detection. We're supposed to write uh, a function to detect the edges in directions. Okay, so all this did it from. Remember, this is edge detection, not corner detection. Okay, thanks. So this is edge detection. This is the function we wrote for our edge detection. Let's run that and see. Sorry about that technical issue. Okay, so we're still continuing with the edge detection, whereby we apply the edge detection to the Python. Okay, yeah, so we're still carrying on. Okay, let's run this. I think it produces this window. Then after that, it amplifies it, then detects the images. Okay, so we applied that on two images. I put them here in the slide. Then you can see here container. It gives you a filtered image, then the edges detected in there. Okay, next was the Hof transform. Hof transform though. I tried this one, but I kept getting an error. I kept getting an error. I think I'll correct that later. Haven't had enough time to correct that, but working on it. Yep. Okay, thank you. Okay. Yeah, other than that, thank you so much for your audience. Okay. See you.